Very well, so good afternoon. Today we have a look at the problem of clustering in wireless sensor networks, because it's a kind of recurring problem when you have to design sensor networks in general. Before going to clustering, very quick summary. On where we are and what we are going to do in the next week or weeks. So basically, as I was saying last time, we now have concluded the part on standards overview for wireless sensor networks. And we now dedicate the last part of the course on, let's say, vertical topics, spatial topics, which somehow fall within the main broad world of Internet of Things or wireless sensor networks. And more in details, we have to see three remaining topics. First one is clustering, which we cover today. Then we will have to have a look at the problems of localization in wireless sensor networks. And the last topic will be radio frequency identification, which is basically passive wireless sensor networks. Okay. Let's get to clustering then. So, if you just to give you a bit of context on where we are, up to now we have always assumed that some type of nodes in the wireless sensor networks we are managing is attached to powers. Okay, so it's attached to main power, and we have called this node in 15.4 ZigBee, we have called it PAN coordinator. Okay. In 6LoWPAN, we have called it edge router, and so on and so forth. In any case, we have always had this underlying assumption that one of the nodes in our network is connected somehow to the internet and also is connected to some kind of power supply. Okay, so we can elect this node as the coordinator of the network or as the edge router of our 6LoWPAN network we are considering. Okay? So in other words, the role of the PAN coordinator is pre-assigned or has been pre-assigned in all the application scenarios we have seen so far. Okay? So in many cases, or in some cases, this is not true, which means that either we don't have any node in the network which has battery supply, which have power supply attached from the mains, so all the nodes run on batteries, okay, and or we don't have any, let's say, single internet connection point. We may have more than one. So we may have, for example, a sensor network which is standalone, okay. All the sensors and has some kind of connectivity towards the internet. For example, they have a GSM, GPRS, 3G module. Okay. So our final goal is to extract information from this network, deciding who is going to be, or if it's, let's say, efficient to have one single collection point of information to be elected as cluster head or as PAN coordinator. Okay? So clustering basically is the problem of what you have to do when the role of the PAN coordinator is not covered yet. So there's no PAN coordinator, there's no clear PAN coordinator which can be prefixed, okay, before network runtime. So basically, the problem of clustering is not specific to sensor network. You know, it comes from other fields. okay, ranging from optimization to other kind of fields. The general kind of outcome or target is to create clusters, which means that given a kind of network topology, a bunch of nodes, okay, we want to divide these nodes into what we call clusters, which should fulfill some kind of properties. And for each one of these clusters, we want to elect one cluster head. So one, let's say, superior node, which has the responsibility to manage each, its own cluster. That's very kind of generic and high-level definition of clustering. So why is it useful? It's useful for several reasons. One reason we have briefly already touched in what we have said so far. For example, if you are running a network which is, monitoring the habitat of some kind of animals, okay, where you cannot afford to have a power supply brought to for example, the wood, okay. So your network is composed of only battery-operated devices. In any case, you want to extract out of this network information on how your animals are behaving. So you may want to elect one of the nodes, which are there in the wood, in the forest, as a cluster head, to collect the information from the other local sensor nodes, and then send information on kind of different link, remote link towards your sink. Okay? If you're in this kind of situation, you face a problem on how and where to place your cluster head. So who is going to be the best cluster head? So the best node which collects information locally and then sends the information to node. Okay? Other reasons why clustering is useful is to, let's say, ease up life for min-max control. Why? We have mentioned that the channel, the medium, is shared among multiple sensor nodes. So we might have problems of collision, congestion, and so on and so forth. One idea to reduce, for example, the collision probability or the congestion probability could be to, let's say, divide your network in multiple subnetworks, each one being one single cluster. So, for example, I may define out of a single network 3 subnetworks, 3 clusters, and let each cluster work on a separate frequency channel, such that the congestion collision is confined into each single cluster, which hopefully has lower number of nodes than the whole network. And then I have to manage, though, in some way how these clusters are created, which channel to be assigned to each cluster, and how then to manage the inter-cluster communication. Okay? So, to ease up the design of min-max control, to make min-max control more efficient in terms of collision probability. Clustering is, in many cases, highly coupled with routing. Why? Because if you cluster a network, if you apply clustering to a network, you are automatically, I would say, defining routers, automatically defining which nodes have to perform some kind of routing, which are the cluster heads, which in most of the cases collect information from the local cluster and then convey this information somewhere else. So clustering is, in many cases, tightly related to routing. Okay? The cluster head is also the router which has to handle the traffic which comes from each single component of the cluster itself. Okay? So basically, you can apply clustering to ease up the maintenance and the management of your network setup. Okay? Again, provided that there's no other reason why there's no other reason which somehow forces you to have one single clear pan-coordinator of cluster. Like there's one single node connected to the internet, or there's one single node connected to power supply through the mains. Okay? So, a very short disclaimer. There are a lot of, let's say, very many clustering solutions available in literature and implemented in practice. Also because, as I was saying, clustering is kind of a topic which is which spans different fields of study. Okay. Today we just see one of these clustering schemes, which is basically one of the first ones. And starting from this first one scheme, many others came. So they all share the same approach as the one we see with this leech kind of clustering problem. Okay. So we see this leech, which is a clustering protocol specifically designed for wireless sensor networks. As I was saying, it's kind of old, so it's 10 years back, 2002. But still, it is mostly leech itself, or some variants of leech, are the ones which are nowadays used most frequently in sensor network for handling clustering. Okay. So the idea is very simple and stupid. Problem is, I have the network, which is I have a bunch of sensor nodes, and I want to decide how to divide this network into clusters. However, I don't want these clusters to be fixed, but I want that each cluster, or better, the role each node plays in the network at different time is somehow time changing. So why we don't want to have one single and fixed clustering scheme for it? So what's the drawback? So what I'm saying is that the problem is to take your network and chunk it into clusters, meaning defining groups of sensors which logically belongs to different clusters. However, we don't want to keep this subdivision fixed forever in time, but we want to change it over time. Meaning that the same node may belong to a different cluster as time goes on. Why? So which are the pros and cons as usual? So the advantage of having a fixed cluster architecture is that you just cluster once. So you just run your algorithm for clustering once, and then that's it. You keep it forever. So what's the disadvantage of having a fixed clustering architecture? So what do you lose?
See the fact that it's fixed is an advantage.
Why?
Because if for some reason some of the node breaks, we cannot do anything to solve it dynamically, but we have to recompute all the process of clustering.
Okay, so any kind of fixed hierarchy architecture is more prone to failures. That's a generic statement which is true independent of whether we are talking about a web server, a clustering scheme, or other. So anything which is fixed is more prone to failure. So if anything goes wrong, your whole architecture is down. That's true. So this is one reason. Second reason is if you fix the clusters, which means if you fix the cluster that rows, it means that you are somehow putting an extra burden of processing, computation, and so on and so forth on all the cluster heads. And these cluster heads, if they're fixed over time, it means that these nodes, they will be the first one which will deplete the energy. Okay? On the other way around, if you change cluster over time, it means that you're changing cluster heads over time. So it means that basically you are forcing all the nodes to share a bit of the energy dissipation, energy burden for processing, computation, and transmission, okay, such that you prolong the network lifetime. Is it clear? So we are a small network. Suppose that I act as a cluster head for a long time, which means that your request gets back to me, and then I forward this request to someone else. Okay, suppose that my battery is limited, so if I'm acting as a cluster forever, it means that I will be the first one who dies here. Okay? On the other way around, if we select, randomly, and as time goes on, a different person to collect information and send information somewhere else, we are actually sharing the energy burden, which means that the network lifetime, okay, will be longer. Clear? So, what Leech does is defining a distributed way which, as time goes on, chooses cluster heads and, as a consequence, cluster, okay, in such a way that they change over time. Clear? So the final architecture is that I have my network, which is made of these colored bubbles here. And what Leech does is to choose one of these colored bubbles to be a cluster head, a bigger ones, for example. And these cluster heads, what I do is to manage the full traffic which is generated by the local cluster components. Okay? More than that, the cluster heads are the ones which are then responsible for delivering the traffic which is generated locally up to a sink. Okay, which can be a PAN coordinator, which can be, I don't know, this link can be a long-range, long-distance link, a 3G link, okay, a Wi-Fi link, or other. Okay? So, the main goal is how, out of these, for example, 4 nodes, how to choose one to be a cluster head, and how to swap the cluster head role as time goes on. Okay? Clear? So, this Leech thing goes on in 2 phases, which repeats periodically. The first phase is a setup phase, or clustering, or cluster definition phase, and the second one is a steady state phase, where clusters are kind of defined. In the setup phase, which is phase to build up clusters, okay, this cluster creation phase is totally distributed, which means that there's no one which tells anyone to be the cluster head at any given time instant. On the other way around, who is playing the cluster head role is decided in a distributed way. Okay, and the procedure is this one. So all the nodes, in principle, can act in Leech architecture as cluster. So they can all be cluster heads. Okay. Then, when the setup phase starts, so when the cluster definition phase starts, all the nodes, they just throw a random number between 0 and 1. Okay. And as we will see, depending on the number they will draw, they will elect themselves as cluster head or not. Okay? So that's very simple. The setup phase starts, everybody can be a cluster. Okay? So everybody draws a random number. Okay? Depending on this random number, according to a very simple policy, the node himself elects himself as a cluster head or not. Okay? And this policy for cluster head election is defined by the equation you see in the slide. So this equation here defines a threshold, which is called E of n, okay, which basically is used by the sensor node to decide whether to elect himself as a cluster head or not. So the node has drawn a random number, right? Then the node compares this random number from 0 to 1 against this threshold, P of n, okay? And if this random number which it has drawn is lower than this threshold, then it can behave as a cluster head. So it elects himself as a cluster head. Clear? Draw a random number, I have a threshold, very mechanical procedure. If the random number is between 0 and this threshold, I behave as a cluster head. Otherwise not. Okay? So let's have a look at what this threshold is. So this threshold depends on a bunch of parameters, actually 2 of them. The first one is P, okay, which is the probability for a node to be elected as a cluster head, or let's say another meaning of P is the fraction of nodes in your network which you want to act as a cluster head. So P is a design parameter which is set by the network operator, let's say, which tells the nodes what's the fraction of nodes which at each phase have to act as cluster head. Clear? So for example, if P is 0.5 and I have 100 nodes in the network, it means that on average the network designer wants that 50 nodes act as a cluster head at every run. Clear? So P is somehow a parameter which is hard-coded into each clustering process. It depends on the network which you are considering, it depends on the types of performance you want out of the clustering, depends on the overhead you want to have. Okay? So if P is 1, it means that all the nodes in the network are clustered. Okay? So you're not clustering. If P is very low, it means that you are clustering, you're not clustering the other way around. So basically you want a single cluster, one single cluster all the time. Clear? So this is the P parameter. Then in the formula here you have also the R parameter, which is a number which is counting the number of rounds of clustering which you have performed. Okay? So basically R keeps track on how many times you have run the clustering phase so far. Okay? And what this formula does, which you have to apply to, all the nodes which do take part in the clustering phase are all the nodes which have not been elected as cluster head so far, where so far is basically up to round R, so the current round. Okay? So the idea of this formula, of this threshold, is actually to increase this threshold, so to increase the probability that a node is elected as a cluster head, okay, as the clustering phase goes on and on. Clear? So if one node is, let's do some checking. Suppose R is equal to 0. So we are at the first round of clustering. Okay? If R is equal to 0, okay, and let's say P is equal, you choose a value, let's say 0.5. Okay? So 50%. This is 0 mod 2, okay, which is 0. Clear? Which means that basically in the first round, at round 0, okay, this threshold is equal to 0.5, which means that on average, half of your nodes will choose to be clustered and half not. If you go on with the rounds, okay, this threshold increases. So for all the nodes which have not been elected as clustered so far, this threshold value goes up, which means that the probability for being elected as cluster head increases. Okay? Clear? And then this process goes on, okay, basically on a periodic base, and in the end, what happens is that out of the round, which is composed of 1 over p, let's say sub-rounds, okay, on average, all the nodes have been elected this cluster at least at once. Okay? So basically, let's stop here for 1 second. Basically, a few observations on this clustering rule. As you can see, this clustering rule does not depend on anything. Meaning, it does not depend on any physical parameter of the network. Here, the only parameter which somehow influences this clustering rule is the p parameter, probability or the fraction of cluster at which you want. Okay? So what do you think of this kind of clustering rule? Remember that this somehow defines how many cluster heads, so how many clusters are in place every round. And who is going to be the cluster head? What do you think? So the first, let's say, first observation is it somehow simple to implement or not? What kind of overhead you have? So each node to implement this rule has only to maintain, I would say, a couple of counters. Sorry, a variable, a parameter, and a counter. The parameter is p, to store p, right? And then the counter is to store r, so the current round. So it's very, very simple and easy to have this kind of clustering rule working on sensor nodes, because the logic is very, very simple and stupid. Okay? What about drawbacks? What you don't have here? Okay. Why would it be helpful to have it in the clustering phase?
Because each node is independent to the other. So if the topology is focused on one part, it's not well organized.
Okay, so it's a policy rule which does not consider in any way the network topology, which means, for example, how distant, how far is one node to another node, okay? Or how much power a node needs to put out an antenna to reach the cluster, for example, okay? So the underlying assumption here is that all the nodes are the same, and the network topology is kind of uniform, even distributed. What else is missing? What else is missing?
How to select from all the cluster nodes that is included or be identified to be in the range of cluster head? How can to choose the first one?
Okay, this is included, we'll see in next slide. Let's just focus not how to then select the cluster head, but let's now focus on the efficiency of this selection rule for the cluster, assuming that all the nodes then magically are assigned to the cluster head, to one cluster. So what is missing only in the procedure for selecting cluster head here? Network topology, as you were saying, what else? So always remember that we're talking about sensor nodes, right? And remember that one of the reasons to apply clustering was to prolong network lifetime. Okay, so what is missing? Does this kind of policy prolong network lifetime for any network deployment or not? No, why not? What's missing? What do you mean by power?
I mean, maybe it's better that each sensor consider its remaining power.
Exactly. So basically, this selection rule disregards completely the battery storage. So current level of the batteries each node has. Or in other words, it assumes that the network starts in such a way that all the nodes share the same battery level. Okay? If this is true, I mean, if all the nodes have the same battery storage or battery capabilities, okay, this is fine in prolonging network time. If the network is not homogeneous from the battery point of view, meaning some nodes has more power than others, okay, then this is not the policy which for sure prolongs network lifetime. So you should include somehow in the network, in the cluster head selection process, the concept of remaining energy. How? Any idea? Huh? Okay. How would you do it practically? Just by hacking this threshold here. Just, rule of thumb. The more power you have, the more energy you have, the higher should be your threshold, right? The lower your energy, the lower your threshold. So basically, the hacking would be just to multiply this kind of threshold through some kind of linear function of the remaining power, properly scaled down by some factor to bring it back to infinity 0, 1, right? So I was just anticipating some drawbacks of Leech because Leech assumes to be working on uniform topologies, both from the network point of view and from the battery point of view. Okay. Then suppose that we have the cluster head running, so we have identified who is the cluster head at every run. Okay. Then, as your colleague was saying, we need to implement this clustering, which means that who is the cluster head should start behaving as a cluster head, and who is not a cluster head should somehow choose one cluster head to be associated with. Okay? So, and that's the flow chart, which is taken from the paper. At a given round, meaning after the cluster head selection process has finished, okay, a node can be a cluster head or not. If it's a cluster head, meaning if it has drawn the random number and this random number was below the threshold, then it elects himself as a cluster head, and what it does is start announcing its own cluster status, which means that there is one specific message in each for cluster head announcement. It's a broadcast message, which is basically telling the other guys, look, I'm the cluster. I am a cluster. Okay. If you want, this is kind of equivalent to a beacon slot, a beacon message in 15.4 implementation. Okay. Then, what it does, it's a cluster head. It has to wait for messages, explicit messages from non-cluster head nodes for joining the cluster head. Okay. So it's kind of getting these messages, okay? And then this is, let's say, the operative part, so to decide what kind of access scheme to put in place within the cluster, okay? In this case, I mean, in that paper, they were proposing to use some kind of TDMA minimum access control within each cluster, okay? But this is not, let's say, related to the clustering process, meaning you can do whatever you want whenever you have your cluster, and you can do whatever you want in your own cluster. For example, one very interesting thing could be to run 15.4 within each cluster, being each single cluster head acting as a point coordinator. Okay? And then in the other branch of this flowchart, you have what non-cluster head nodes do, which is basically they have to wait for someone declaring himself to be a cluster head. So they kind of receive multiple, let's say, cluster head announcements, okay? And then they have to decide to which cluster they want to be somehow part of, okay? How would you do it? So which one would you choose? So in some cases, it might happen that one non-cluster head node receives announcements from multiple cluster heads. Okay. So which one cluster will you choose? Or what could be a nice policy to be used to decide which cluster head to be used? For example, I may want to choose the cluster head which I hear stronger. So whose signal I'm hearing with the highest power level. Why? Because we're closer, because it's just transmitting with more power and so on and so forth. The link is kind of more reliable in that sense. Okay? So once I've done my choice, I have to send the explicit join request message back to the cluster. Again, it's a message. Okay? And then at this point on, it depends on the specific medium access control which is put in place. If it's TMA, okay, I need to have a feedback from my cluster head to tell me what's the structure of the medium access control TMA-based approach. Okay? Example, if the medium access control within one cluster is 15.4, okay, this guy here, or all the non-clustered nodes, will have to wait for the beacon, which tells them what's the frame structure, what's the beacon interval structure, what's the GTS, what's the cap, and so on. Okay? So as you can see, clustering can be used in composition with what we have seen so far. So it can be used in composition with 15.4 as an underlying medium access control protocol. Okay? Questions? Okay, so this is kind of something we already mentioned. Just one additional observation. When the clusters are there, communication happens. What do you call it? Communication in Leech happens only through the cluster head, which means that in principle, cross traffic between non-clustered nodes belonging to the same cluster, okay, it's not possible. Just like in 15.4, you always had to go through the PAN coordinator. Okay, the same here. This is not, let's say, a rule written in stone, in the sense that it could be possible, okay, to enforce also cross traffic within the same cluster. But in the plain implementation of Leech, this is not possible for all the reasons which we already know, like simplicity, keeping things simple, going through the cluster. The cluster is much simpler than handling kind of routing table entries for all the nodes in the same cluster. Okay. So in the end, visually, what happens is that basically you have a bunch of nodes, okay, in your network, and what this figure is showing is basically the result of two consecutive clustering phases. So in the first phase, on the left-hand side, these guys here were elected to be cluster heads. And what you see in these thicker lines is basically the geographical composition of the clusters. So all the nodes which fall, for example, in this area here, belongs to this cluster head here, and so on and so forth. This is called Voronoi tessellation, just a name. Okay? Then, after one round, so these guys has run the clustering process, all these guys have waited for cluster announcement, and they have decided which cluster head to be associated to. Then they start doing traffic, okay? And then after some time, which is protocol specific, the cluster head selection phase is rerun. And this is the result. So this is a new cluster head, and so on and so forth. Okay? Just by chance, the results of these two cluster head selection phases have output the same number of cluster heads. So you have the same number of cluster heads here and here. Okay, this is just by chance, because Leech also only ensures that on average you have a fraction of cluster head running in it. So it may have happened that here you have 10 cluster heads with respect to 5 in the previous one, and vice versa. Okay, clear? Questions? And here I guess that the rule to be associated to one specific cluster head was the distance. Okay, so the received signal strength. Okay. Okay, that's basically a more detailed description on the association phase, which is kind of clear right now. It only requires additional signaling messages, which is the advertisement message from the cluster head, the announcement message, what we call announcement so far from the cluster head, the join request from nodes, and then the schedule indication, which is basically the signaling message from the cluster head to the cluster, non-cluster head node, which is telling the non-cluster head node what kind of medium access control has to be run. Okay, a TDMA schedule, a beacon message, or other kind of signaling message which are medium access control specific. Okay. Then, as I was saying, the cluster head selection phase has to be repeated over time, and that's a kind of problem, in the sense that it's not a problem, but it's a kind of dimensioning problem, in the sense that you have to decide from the network operator point of view, okay, how frequently you want to refresh your cluster head situation. Which means how long, what's the frequency of the running the cluster selection phase. Or conversely, how long the steady state phase you want to be running. And again, this is a parameter which depends on a specific application you have to put in place. So what kind of traffic you have, what's the frequency of the traffic you have, what kind of topology you are considering, and so on and so forth. Okay? So if you want to design a clustering algorithm following Leech policy, the parameters you have to decide are basically two, I would say. First one is the P, so the fraction of cluster heads you want up and running all the time. And second one is this, clustering frequency. So how fast you want your cluster to be refreshed. Okay, we have already mentioned what's the trade-off in the decision of P. The trade-off in the decision of the clustering steady-state phase, the length of the clustering steady-state phase, is that if you do it too long, you're not clustering, in the sense that it's just like you are running a fixed clustering architecture forever. Okay. If you do it too short, you are more responsive in following, let's say, the energy depletion in your network, for example, but you are requesting the network to run signaling procedure more often, which means that you are trading off energy efficiency against the signaling burden. Okay. So again, the trade-off choice depends on your specific situation. Okay. The other problem is that in Leech, you don't basically have any design guidelines on how many clusters you want to have. So how to set your P parameter. Okay. The drawback is basically if you force your network to have very few clusters, most likely the non-clustered nodes will be far away from the cluster head, which means that they may have, worse link quality because they are more far away. Okay. Or conversely, they need to convey more power to the antenna to reach the cluster. Okay. If you have too many, you are basically putting energy burden onto too many nodes, which are cluster nodes. So you are defining nodes which collect traffic and send traffic, so you are actually defining more energy bottlenecks if you have multiple clusters. So again, the choice here is a trade-off between your needs and the efficiency performance KPIs which you need to put in place given your specific network topology. Okay? Clear? Questions? Okay, this was all about clustering. So as I was saying, I just kept this kind of for the reason we already discussed before. So because there are very many clustering solutions available. So my, let's say, goal was just to give you the instrument, the tools, such that you can go out there and, make up your mind on the specific solution which you may find. Okay. All the solutions follow the same approach as Leech does. So they have a steady-state phase, they have a clustering phase where they decide somehow how to cluster, and then they have a steady-state phase where they implement some kind of medium access control protocol within each single cluster. Okay. For example, there are solutions which, besides implementing different medium access control protocols inside each one cluster, they also use, as I was mentioning before, different frequency channels inside each one cluster, just to reduce the interference which is caused onto or towards nearby clusters. Okay, so I would say the most common approach which you find for clustering is to apply some kind of clustering policy, like Leech is one, and then assign frequencies to different clusters such that the interference is lowered. Within each cluster, then, as I was saying, you can play with different medium access control protocols, but in most of the cases you do 15.4. So inside each one single cluster you implement beacon enable 15.4 because it's the easiest. So that's the let's say the most common stacked up architecture which applies clustering on sensor networks which I've seen running in reality. Okay? Questions? Okay, so since time allows, we have to move on to problem of localization, which is kind of a very hot topic nowadays, because there are several technologies which allows to get information on the position of an object, a human being, or other kind of moving entities. And because out of this information, you can build out several services which are often referred as location-based services. Have you heard about it? So for example, if I'm able to track you, okay, and if I get to know that you are close to some kind of shops, I can provide you some kind of targeted advertisement service saying, look, this shop has this kind of offer. I know that you are interested in running shoes, for example. Okay, so why don't you go there and have a look at these running shoes? So all these services, which are called context-based services or location-based services, are based on some type of localization underlying service, okay, which knows where you are and uses information to convey additional information to you, okay? So that's why localization, so if you are a kind of expert in localization, or if you want to go more in details on how localization is performed, you have a huge market out there. So you can actually resell your expertise in several kind of different fields. Okay, and that's why I have this special topic on localization here. Okay. So what is localization? Basically, localization is about determining the physical position of some entity, okay, with respect to some type of what do you call it, coordinate system, okay. And usually, this kind of process or problem is solved by, or better, through leveraging the presence of what is called anchors or anchor nodes, which are basically static nodes which are out there in the environment, which are used to, again, localize. The most classical example is localization through GPS. GPS is the localization system based on satellites which play the role as anchor nodes, which are not here on the Earth but are in space. And using the information which is provided by these satellites, you can actually localize the position of nodes on Earth. Okay? That's a kind of general and again generic definition of localization. Okay? So let's see which are the ingredients of designing any localization system. So the first ingredient is basically the object which is to be localized or not. Okay, and the distinction on the object to be localized or not is whether the object or the entity to be localized can carry some hardware or not. So does this guy have a transceiver with himself or not? If it has it, so if it has a piece of hardware which can be used by the anchor nodes to localize himself, this is called an active localization system. Okay? Active because the entity, the human being, the animal which is to be localized carries a piece of hardware which interacts with the anchor nodes. Example, the GPS system, to be localized with GPS, you need a GPS transceiver. Okay? In your clock, in your navigation system on your car. So this is active localization system because the anchor nodes, okay, interact actively with the receiver or transceiver which is mounted on the person or on the vehicle or on the entity which is to be localized. Okay? So in active localization system, there is an interaction which is basically an exchange of messages between anchor nodes which are fixed somewhere in space or on the Earth and the clients which needs to be localized. This interaction happens through some piece of hardware, GPS transceiver, 15.4 sensor nodes, Wi-Fi sensor nodes, and so on. Okay. Then, if this interaction is in place, so if we are talking about the active localization system, the localization, so the knowledge of the position of the client node, okay, is somehow obtained by measuring from the anchor nodes what is the quality of the signal which is exchanged between the anchor nodes and the piece of hardware of the entity to be localized. Okay? So in active localization system, I have something which is sending a signal to the anchors or vice versa, and depending on the quality that these signals has at the anchor nodes or at the receiver, so the client node, then the localization system can infer what is the position of the client which is moving. Okay, so that's again a very general kind of building blocks definition of a localization system. We'll see how and what quality means, what kind of anchor nodes we have, and so on and so forth. Clear? In passive localization, you don't have a piece of hardware on yourself or on the object to be localized. What you have usually is only the anchor nodes. Okay. So basically, in passive localization, you cannot exploit any signal which is explicitly exchanged between the client to be localized and the anchor nodes. So you have to do something else. Okay. So what is best? Pros and cons of the two. Active localization and passive localization. The common background is that you always have these anchor nodes out there. Okay, which do something. In active localization node, these anchor nodes typically send beacons which are received by the client or vice versa. Okay. In passive localization node, they are only hearing something. Okay. What is best? What kind of scheme is better in your mind? It depends. So which are the pros and cons? Let's talk about active localization. This active localization is kind of invasive, which means that you have to give one person a piece of hardware to be localized. So if you want to localize animals, you have to give a piece of hardware to animals in colors and this kind of stuff. So it's more invasive, I would say. In passive localization, it's totally hardware free. So basically, you can track people without any, let's say, without the need of giving people anything, okay, in a passive way. So from this point of view, passive is much better, right? It's much less invasive. The drawback is that passive localization systems are not that accurate. And more than that, in passive localization system, you can hardly recognize one specific instance from the client you want to localize. Let me rephrase it. I say it in a very, very bad way. In passive localization system, you cannot identify. Okay? Most likely, you can just say that there's something which is at some position, but you don't know what this something is. In active localization systems, since the client has a piece of hardware, okay, you can actually localize and identify the specific client which has that piece of hardware. Okay? Clear? Okay, so let's focus a bit more on active localization systems, which are the most diffused one. Okay? And let's have a look at how the position can be inferred out of the quality of a signal. Okay? So there are different types of active localization systems, or better, you can classify active localization systems depending on different criteria. The first one is the technology. So what kind of interaction happens between anchor nodes and the client node? What kind of technology can we use to localize? So you have basically three types of technologies which you can use. The first one is RF, so wireless transceivers, okay, which can be Wi-Fi, Zigbee, ultra-wideband, or others. The second one is audio, so you can use ultrasound to localize. Okay, and the third one is infrared, so you can use this kind of infrared technology to localize. Okay, so these are the most common three technologies which can be used to handle the exchange of information between the anchor nodes and the client node. Okay, then you can basically, regardless of the specific technology which you're using, you can decide what kind of quality measure of the signal to be used to get information on position. And also here there are basically three types of quality measures which you can use. So what kind of input data you want to use to localize. The first one and most common one is the RSSI, so the received signal strength, or the received signal indicator, so the power, the received power. The second one is the TDOA or TOA, okay, which is basically the time of arrival. So they're not measuring how much power is being received at the receiver, but they're measuring what's the delay from the time the signal was sent to the time the signal was received. Okay? And the third one is the angle of arrival. So they are measuring what's the angle the signal was received with the highest gate, basically. So what's the angle of the arrival between the transmitter and the receiver? Okay? Let's stay here for 1 second. What is the, let's say, easiest one, the easiest measure to be used and implemented to localize among the three? The first one, right? Or let me change the question. Why the second kind of measures are more difficult to use to implement?
I think you need synchronization.
Right, because you need synchronization, right? So you need sender to be synchronous with the receiver, which means that the client who is going around with this piece of hardware needs to have the same clock as the sender, which is somewhere in the environment. This is doable, obviously, but these things here are more expensive, okay? And plus, they have some, let's say, drawbacks, which we'll see next. Okay, so you can decide which technology to use, which signal out of that technology to use, and then you can also decide what kind of signal model to be used. So what kind of model to be used to get out the positioning information out of the signal you're using. Okay? And here you have two kinds of approaches. The first one is a parametric one, and the other one is a non-parametric one. I guess that the classification in terms of technology and type of data which is used is clear, right? Let's focus 1 second on this classification here, okay? And let's start seeing what is parametric localization models, or systems. So let's focus on parametric system based on RSSI. So we want to localize out of the received power, and we want to use this kind of parametric model. So in parametric model, what you do is basically to assume that you know a priori the relation between the received signal strength or the received power and the covered distance of the signal. Okay? So the objective here is to get out the distance between sender and receiver out of the received power. Okay? In parametric model, what you do is to somehow assume that you know what is the relation between the power and the distance. So how power propagates in the environment. Okay? For example, one of the most common model is the one you see here. So basically S is the received power, and D is the distance. S0 and D0 are just parameters of this model, just like, I guess it's ni, right? Qualcuno ha fatto il classico? Ni? I guess the name of that variable is ni or nu, I don't remember. I did scientifico, so I'm allowed not to know.
No.
Huh? That's for sure wrong. That's wrong for sure. So you did itis, right? Okay, good. But you are allowed not to know. Okay, I mean that thing there, let's say. This is a parametric model because it's based on parameters, which is basically this variable there, ni nu, okay, which expresses the propagation environment like fading, shadowing, and so on and so forth. That's not important as we stand now. What is important is this path loss exponent, which is basically telling us what is the decaying rule, which tells you at a given distance what's the received power out of a given transmitted power. Okay, and these models here are, let's say, most likely exponentials, which means that the received power decreases as a power law with respect to the distance. So the received power decreases with d to the minus alpha. Okay? The formula here is expressed in logarithmic form. That's why you just sum up things. You don't just multiply. Okay? So, this is something you know, or better, this is something you assume to know in your localization system. Okay? And since you know this kind of, since you are inferring, conjecturing this kind of dependency between power and distance, if you know the received power, which is S there, you can invert this formula and get out D. So get out what is the distance from the transmitter to the receiver. Clear? Is it clear? So what's the problem of these models? The problem is that basically you don't know exactly what is the propagation model, which is out there. Is it clear? Let me rephrase a bit. The problem is, I know what is the received power at a given point, and I want to have knowledge on what is the distance between the receiver and the transmitter. Okay? If I know this distance, then I'm fine because I can trilaterate, we'll see how, and I can find the position. So my first problem I have to solve if I want to localize is to invert power with respect to distance, or vice versa. Okay? This approach tells you assume that the relation between power and distance is such. So it's given by that model. Okay? If this is true, given a certain power level, you can get out what is the relative or corresponding distance from transmitter to receiver. And then you can then localize as we will see. What is the problem? The problem is that this is an assumption, so it's not true, or it might not be true, that power and distance are related to that specific parametric model at a given time instant. Why? Because environment may change. Okay, so the propagation model, which is right here, right now in this room, is different than what you have if this room is empty, for example. So you have different relation between transmitted power with received power and distance if this room is full or empty. Okay. So if you think let's say, from the perspective of who has to design a localization system, okay, this guy wants this localization system to work well regardless of specific environment condition. So regardless of the fact that this room is too full or empty. Okay? Which means that this kind of parametric models are kind of averaging over different kind of conditions. Okay? So they may have, they just tell you that on average, propagation law is such, which means that transmitted power with respect, received power with respect to transmitted power is modeled for this kind of approach, on average. Which means that if you take a measurement on a specific time instant, the current propagation model might be totally different. Which means that what you are telling, what you are getting out of this parametric model, the distance value you are getting out with respect to the parameter model may be totally different than the real one. Okay? If the conditions are far from the average. Is it clear? Okay. So then what you do with these parametric kind of models? Okay, you have these n anchors which are there. So remember that these n anchors, these anchor nodes are assumed to be always there. Okay, passive or active localization systems. Then what you have to do to localize, suppose that, I mean, this here shows you 3 anchors, for example. What you have to do is to collect some measures of received signal strength between anchor nodes. Okay, so without the client to be localized, you first collect signal to receive signal strength measures out of transmission between anchors, just to estimate what is the environment. So to get to know what kind of parametric model to use. Okay, and then you have your clients in the system. So you, for example, you have any client node. And what you do is to collect RSI measurements between client nodes and anchor nodes. Okay? So from the client to the anchor or vice versa. Okay? And basically estimate what is the distance between each one client node, from the client node to each one of the anchors the clients over years. So you get actually an estimate of these R segments here. And how you do it is just by inverting that formula, D, out of the received signal strength, which is S. Okay. And then if you know these 3 segments, or better, you know the n distant segments from all the anchor nodes, you can just invert. So you can just find what is the intersection between these 3 circles, which is the position of the client. So that's the ideal localization system. We'll see how and why it is ideal. Okay? Just a couple of observations. First one is who sends and who receives. Basically, this very same system can be implemented by letting the anchor node sending beacons down to the clients. So being the clients the one which receives the signal and then estimates the distance, or the other way around. So it can be the client which beacons up, and all the anchors which overhear the client, they can invert their own, let's say, distance with respect to that client. Okay? More than that, the localization engine, so the localization algorithm which finds a position out of the distance, can be run at the client, okay, or it can be run somewhere else. Clear? So these are basically design choices here. Is it clear? Okay, so which are the advantages and disadvantages? Advantages of this kind of parametric RSSI-based model are basically simplicity. So that's very easy to implement. You can do it even with off-the-shelf Wi-Fi hardware. Okay. Cost. You can do it with very, very stupid and naive transceivers like ZigBee, Wi-Fi, and so on and so forth, which cost very few dollars or euros. Disadvantages are on performance. The accuracy which you can get out of these systems, we'll see how, they're not that good in the sense that you get an accuracy or, let's say, an error in localization which is in the range of 2 or 4 meters. Okay? So if you are here, and if you are in this position and you apply one of this method returns to a position which is on average in a circle of 2 meter range radius pointed in the real position. Okay, so you have an error of 2 meters in localization fields. Clear? And this error, as we will see, is mainly due to the fact that you are using an average parametric propagation model. Okay? Which is not exactly how power and distance are related at the very time you need to localize. Okay? Clear? Okay. The other possibility is using non-parametric RSSI-based model. Okay? And that's it's even simpler than parametric ones, because what you do in this case is to obtain what is called a fingerprint of the environment. Example, you have several anchor nodes in your environment, okay, and then what you do is to go there with a probe, which you can control. So with a transceiver, with a fake client to be localized, which you can control, place yourself at one position, which you know, X and Y, and register what is the RSSI which you receive from all the anchors. Such that you can populate a database which tells you when you are in this position, X and Y, that's the fingerprint, so that's the signature you're receiving out of your N anchors. Then you move to another place, X and Y, and you do the same thing. So you do what is called a site survey. So you survey your site you want to localize, and you store in the database what is the RSSI vector you are receiving out of all the anchors for a given position, which is probed, which is given. Okay? This is a site survey phase, and then you have to localize. The localization phase is much easier in this case because when a real client gets in your environment, what the real client has to do is just to measure the RSSI vector which it is receiving in a given position, send this vector up to the localization engine, and what the localization engine does is just to match this vector against the database and returns you what is the closest stored vector with respect to the one which has been measured and the corresponding position also. Okay, this is called fingerprinting, localization by fingerprint. What's the advantage? Advantage is again simplicity, and with respect to the previous one, you can do this kind of localization by using networks which are already there. So you don't have to deploy your own anchors. For example, you can use fingerprinting using the Wi-Fi network of Polini. You just go there, measure what's the receive signal indicator you're receiving out of the, what do you call it, Polini access points, okay, and then you can populate your database. In other words, you don't have to deploy a network infrastructure which is dedicated to localization, like in previous case. Which are the disadvantages? Again, accuracy, because basically this kind of localization system has accuracy which is comparable with respect to parametric one. The reason is basically that they're using the same input data, which is received signal indicator, which is basically not that reliable, as we will see in the next slides. Site survey is required, which means that this is basically a database-based localization system, which means that to run properly, you have to populate in advance a database of received signal indicator versus X and Y position. Okay? Which is costly, which means that you have to pay at least one person to go there and do these tests, hopefully with a high granularity, so a kind of every meter on a grid of 1 meter step at least, which is again a costly kind of procedure in terms of time and money. And more than that, it's not that flexible because as I was saying, propagation condition may change over time, which means that you would have to repeat this site survey several times during the day just to be sure that the database you are populating reflects the current status of your environment. For example, if you are talking about a shopping mall, a supermarket, you should have a site survey when the supermarket is full, when the supermarket is kind of average full, when the shopping mall is totally empty. Such that you know what is the database you have to use for a given point, at a given point of time to get out information on localization. Okay? So it's kind of not flexible in the sense that you have to redo the site survey whenever something changes in the propagation environment. With respect to the parametric one is an average model. So basically it's just telling you on average this is the propagation model which you have to use. So you don't have to somehow worry too much about the changing environment because you are averaging all in that model. Clear? Questions?
How to choose points for the inside survey?
How to choose what?
Points. For example, in which points should you do it?
Let's say, how would you choose it? Let me reverse the question. How would you choose the points to survey in your site survey? You can choose it a kind of uniform way. Just take your, the map of the environment and overimpose a grid of a 1 meter step, and then do it for all the points you have. Or what else? It really depends on what's the, what do you call it? What's the environment. So if I have, I don't know, let's take the shopping mall example here. In the shopping mall, you have shelves, right, with narrow corridors, okay, and then you have some kind of open spaces, like where you have to buy bread or all this kind of stuff, right? I don't know. For example, you could somehow be more dense in choosing the points in the survey, okay, where you want your localization to be more accurate, okay. So if you're talking about a corridor, you don't really need to know exactly where you are X and Y, provided that you know that you are in that corridor, or in a given, let's say, Y dimension of the corridor, okay. The other way around, if you are talking about an open space, you might want to be more aggressive there in the site survey, okay, because you really want to know where is the person in that open space. So the answer is, it really depends on where you want to be more accurate with respect to other positions. And I would be more aggressive, meaning I would choose more points in my site survey in all the positions, or let's say in all the sub-environments where I want to have a higher accuracy in my localization system. Okay, so let me conclude with this localization through ultra-wideband, which is again another kind of common way of localizing. So just to give you the usual placeholder, what we're doing right now is the following. We are just overviewing at a general level which are the localization systems. Okay, so what kind of pieces, components you can use to localize. What we will do tomorrow, I guess, is to go into more details into the trilateration process. So out of the distances which we have extracted using RSSI or other tools, how can you get position? Okay, this is called trilateration. So localization through ultra-wideband. With respect to RSSI model we have seen so far, ultra-wideband uses TOA, which is time of arrival or time difference of arrival information to localize. Okay, the architecture is the same as RSSI-based localization systems. So you have basically anchor nodes, and tags, client nodes. But as I was saying before, the specific quality measure of the signal which is used to localize is the difference of arrival in time, which means that the network of anchor nodes needs to be synchronous, okay, and it needs to be synchronous with the client. I'm showing you this kind of localization system here because nowadays is the localization system with the best performance in terms of localization accuracy. Okay? It can go down to centimeters of precision, which means that you can localize one item with an error of tens of centimeters. Okay? Why is more precise? Because if you have a synchronous network, the signal you're using to localize, which is the difference of arrival, time of arrival, is much less noisy than receive signal strength or receive signal indicator. Okay? Which, as we will see, is more noisy due to interference and such. Okay? So what's the problem of this kind of localization systems? They have two problems to conclude. The first one is cost. So since you have to have a synchronous network, this means that you need to have a synchronization protocol between the anchor nodes, which is costly. Okay? And the second one is that they do not perform well when you don't have line of sight propagation. Okay? So the underlying, I mean, this performance measure you see there, so up to 10 centimeters of error, you can achieve if the anchor nodes and the client nodes are in line of sight. Okay? If they're not in line of sight, you go much higher than only 10 centimeters of error. Line of sight means that there's nothing solid, let's say, in the middle. Okay? On the other way around, the performance metrics which I mentioned to you for the RSSI systems, they are basically regardless you are in line of sight or not. Okay? So these kind of systems are much more precise, they cost more, but they're more sensitive to obstacles and this kind of stuff which you have in your environment. Okay? So which one to use, again, depends on the specific system and environment you are in. Okay? So again, what we will do tomorrow is to see more details on how trilateration or lateration techniques are actually applied to get localization. Okay? I'll see you tomorrow.
Volevo chiederle, ma la lezione di giovedì che non sono potuto venire, ma la metterà sul...
Sì, ce l'ho.
C'è un'esercitazione, cosa fate? Esercitazione a lezione?